Cool. Okay. Can you see a power cord anywhere there? Is there a power connector? That's the closest one I've got.
Yeah.
Yeah.
Your finger doesn't stand.
Well, it probably won't go that far.
When you don't
Yes, it
understand
won't go that far.
anything other than an hour of you.
You know what I do? I put my laptop on here.
Better or worse.
Welcome back, everybody.
My name is Kitaev, and I
Oh yeah, sorry. Is it working now?
Yep, it's working now.
Oh, perfect. And there are some non-trivial topology of the ground state wave functions of these ground states. And so that's why sometimes in the literature, the quantum spin liquids are also called symmetry enriched topological states. And usually there are some spin fractionalizations of the spins. So here, so for example, in the RVB picture, you will have some breaked up spin half spinors. And in our case, the Kitaev model will have some Marana fermions and some Z2 gauge fields. Okay, then let's go to the Kitaev model. So the Kitaev model is, at the first glance, quite bizarre because it has some bond-oriental spin-spin interactions like this. So for example, along this bond, you will only have sigma x coupling, and this one sigma y, and this one ZZ. And Kitaev proposed this toy model just because it can be exactly solved. And well, he has shown that how to do this is to map the whole Hamiltonian into a Hamiltonian of 4 Majorana fermions like this. So 3 of the Majorana fermions are bond-oriental, just like the spin interactions, and 1 sits on the site, so sits on every side of it. And one might just realize that by doing this, by mapping this into 4 Majorana fermions, we are actually enlarging the Hilbert space twice. So we have to address this constraint to go back to our physical Hilbert space. And it also fixed the spin algebra. So after rewriting, we have a quartic Hamiltonian of Marana fermions. And this is still not exactly solvable. And to see that it can be exactly solved, is to further simplify it by defining the the 3 pairs of bond oriental Marana fermions as some, to treat them as some entire operator like this. And one may realize that the bond operator defined here actually commutes with the Hamiltonian. So they can be simultaneously diagonalized, and if you square them, it gives you 1. So the eigenvalues are just plus minus 1. And furthermore, you can just define the Placato operator, which is nothing more than just the product of 6 bond operators along a single hexagon. And this is also a good quantum number. So it also commutes with the Hamiltonian and gives you the eigenvalue of plus minus 1. And this is just like to have magnetic fluxes along each hexagons. So we can define -1 to be, we have a flux at this hexagon, and +1 to be flux free. And then, and then it just, you can just plug in numbers to the Hamiltonian and it gives you a quadratic Hamiltonian, which can be solved. So, I mean, and one thing to address is the ground state. So the ground state we can be sure that the ground state is actually flux free due to this Leib theorem, which, proves that the ground state is like that. And one more thing to realize is that the Z2, the bond operators here are actually Z2 gauge fields. So they correspond to some gauge degree of freedom. So you can see, because the Placato operator here is the only physical observable, so we can pick actually different values for the bond operators along the same hexagon to get the same eigenvalue for the Placato operator. So actually there are some gauge degrees of freedom that we can make use of. Okay, so now we know that the ground state is a 0 flux sector, so we can just, for simplicity, send all the bond operators to have the eigenvalue of 1. Then we have quadratic Hamiltonian, which looks exactly like the electrons in graphene. And by solving it, you will get this kind of honeycomb structure. And one interesting thing is that just like you can add strain to the honeycomb lattice to tune through the topological phase transition in graphene or black phosphorus, if you like. Now, here you can do similar things. So if you add anisotropy in the Kitaev coupling, then eventually, when the anisotropy is large enough, the system will go through a topological phase transition from a gapless Kitaev quantum semi-liquid to a gapped one. So the band structure, the mean field band structure looks like this. So you see that the 2 direct points merge in the middle and then open the gap. And the flat bands here corresponds to the gauge degrees of freedom. And also, Kitaev first proposed this because it's exactly solvable, but it turns out that it can be experimentally realized. So so it makes the problem even more interesting. And in this VRL paper, they've proved that they've showed that in such kind of A2BO3 structure, because of strong spin orbit coupling and the bond cancellation on the oxygen bonds, actually you can have such anisotropic spin Hamiltonian. Okay, so let's go to our work. So in any real systems, there will always be something more rather than just a pure Kitaev. So you have some residual magnetic interactions like Heisenberg, gamma, or BM interactions. So what happens if we have this kind of perturbations, and how will it affect the phase diagram? So we consider the simple case, which is just a pure Kitaev model plus anti-ferromagnetic Ising coupling. The reason we did this, the reason we add this Ising coupling for specific will be clearer later, but nevertheless, the extra magnetic interaction term makes the whole Hamiltonian not exactly solvable anymore. So, and one can just get it by staring at the Hamiltonian that there will be two quantum phase transitions. One is that because, like I said, when you ramp up the anisotropy in the Kitaev coupling, you will go through this gapless to gapped quantum spin liquid topological phase transition.
Question.
So,
Will anti-ferromagnetic and ferromagnetic coupling be the same?
yes, for most of the most region of the phase diagram, they are the same. So there are claims that in the ferromagnetic Ising case, there is another small region that can realize another spin liquid. I think it's a chiral spin liquid or something, but it's only on the mean field level, and there's only a small region which has large J, so it's somewhere here.
I guess my question was, can you transform the positive J to negative J?
Oh yes, of course.
Okay.
Yes. Yes. So, but it turns out the magnetic phase transition from the quantum spin liquid to the ordered phase is actually first order. So this is not our concern here. So we are focused on the gapless to gap one topological phase transition, and one would imagine that because the Ising term looks to the Kitaev Hamiltonian like some sort of anisotropy. So with a finite J, we can also tune the system through this topological phase transition. And to this, we did our mean field theory. So we actually didn't use the representation that Kitaev used. So we actually used the 2D Jordan-Wigner transformation, which is introduced in this paper. Applied to Kitaev model in this paper. And yeah, so by doing this, because I think most of the ones someone here will know that for 1D, the Jordan-Wigner looks perfect. But for 2D systems, there are problem that if you do the mapping, you will get a non-local Hamiltonian. So in order to maintain the locality of the Hamiltonian, we actually have to define this snake-like string operator, which goes like this. And you see, this is exactly why we only add the Ising coupling, because you only have extra ZZ coupling, which stays local in the 2D Jordan-Wigner, and the whole Hamiltonian will stay local. And this gives you 2 Marana fermions instead of 4. So in that gauge field language, actually by picking the snake-like string operator, we are picking a fixed gauge for the whole system. But like I said before, it was just some gauge degrees of freedom, so we can make use of it. Then the mapping is exact, so there's no problem on it. And then we can do the mean field theory on it and get the phase diagram. So the phase diagram look like this. This is the line that separates the 2 topological phase, and this one cuts this one separates the ordered phase and this the liquid phase. And our interest stays on the topological phase transition. So now we confirm that for finite J, we can still have this topological phase transition happening. And if you look at the band structures of the Marana fermions, then for finite J, you can still tune the band, make the 2 direct points close at some point and then open the gap. The only difference is that here, because the model is not exactly solvable, so the gauge fields are not exactly gauge fields. So they actually do have somewhat mobility. So you see that the flat bands are not flat anymore, but they still have a large gap, large enough to make us neglect it before or afterwards. So the fat bands become dispersive. And now we can ask the question, what if we go beyond mean field theory and analyze this, the criticality here? So we go to the path integral formalism and use again the mean field result, which gives us this. And it's just a 4 fermion interaction involving the 2 Marana fermions I've just introduced, one representing the gauge and one more mobile one. And because the gauge fields degrees of freedom and the eta Majorana fermions here are still gapped. So in our low energy field theory, we just integrate them out. And by integrating them out, well, it's just by doing this diagram. Actually, we get a effective full fermion interaction, which only acts on the mobile Majorana fermion. And because of the interaction strength due to the the extra Ising coupling, I mean the C3 symmetry is not actually preserved, but you can group by the strength of coupling these 4 groups of the coupling, but they're always the same. So because bear in mind that these are Majorana fermions, that's why we cannot really have a meaningful on-site coupling. The minimum coupling that we can have is this coupling, which involves 4 different sites.
So why is that the Majorana fermions aren't have meaningful coupling?
Or it's just because they are its own counterparts. So if you write C dagger C, it's just like C dagger, which gives you the anti-commutation relation that gives you a number. So which means that the square of the Majorana fermions is just a number, which looks like a chemical potential, if you like. So it's not, yeah. So that's why for fermion on-site term then gives you a 2 fermion term.
Thank you.
Yeah. So, and the interacting strength actually have this complicated form. But nevertheless, the only thing that you need to know is that it goes to 0 when we tune down the Ising coupling, which means that for the pure Kitaev model, the theory is just a free Majorana fermion theory. And this makes sense because the pure Kitaev model is exactly solvable. So it's at mean field level exact. And if you're familiar with the field theory, then by looking at this, you might imagine that if we do some sort of a Hubbard-Stratonovich on the electron hopping channel, or fermion hopping channel, sorry, then we will have a similar theory like a Grasnover-Yukawa theory, which describes the topological phase transition from a topological semi-metal, direct semi-metal to some ordered phase. So that's the next thing we do. And just to remind you, we now briefly introduce the Grasnover-Yukawa criticality for general. So it's like I said, it's just the criticality just describes the topological phase transition from a semi-metal to a gapped state.
You had 2 transitions. One was the black one between gapless and horizontal.
Yes.
The other one was the red one to the border phase.
Yes.
You're now on the black one, aren't you?
Yes.
Right.
Yes. So we are.
But there is no symmetry.
Yes. Exactly. So, I mean, if we define some sort of node parameter here, but like you said, it's not a symmetry breaking phase transition. So we are just thinking that we have the structure of fermion interactions, which looks like a fermion-induced criticality, but in reality, there's no symmetry breaking at this point. But nevertheless, we think this can still be analyzed in the same manner, like a symmetry broken phase transition. Yeah, so this is the general Grasnover-Yukawa criticality. What you have is some Dirac fermions and some full fermion coupling, for example, Hubbard interactions. And then you do some Hubbard-Stratonovich in the electron-electron coupling channel. And then what you'll get is a bosonic field, which couples to the Dirac electrons. Yukawa-like coupling, which involves a bosonic field and the two Grassmann fields. And of course, for the bosonic field, when you do the Hubbard-Stratonovich, you will also get a free propagator of the bosonic field and the 5^4 term. But actually, for the 2+1 case, because we have this zero energy particle Hall excitations in the Dirac fermions, this actually strongly damps the propagator, the bosonic propagator, which gives you a non-analytic result, which overwhelms this term at large n. So this term can actually be dropped. And if you use the new term as your propagator, then the 5⁴ term is actually irrelevant. So the only interaction you will have is the U-cover coupling. And if we do the, and what the Grosvenor U-cover criticality gives you is just that there's a non-trivial fixed point at non-zero G, which is the U-cover coupling strength. So it's I'd say it's a typical example of a Fermion-induced quantum criticality. And the exact form of this U-cover coupling is determined by which order you might have. So for example, for charge density wave, you will just have a diagonal sigma z coupling, which on sublattices. But for spin density wave, then you will have a Heisenberg-like coupling. Okay, then let's go back to our effective field theory. So yeah, like we have discussed before, there is actually no real symmetry breaking here, but we can still define that. We can still define this two fermion hopping term, if you like, as the order parameter, and then go to the continuum limit and name it as our bosonic propagator, and we'll get a Grosvenor U-cover like theory. And the only difference is that because, like I said before, Majorana fermions can't really have on-site couplings. So here, the matrix structures for the U-cover coupling is a bit different. You are actually coupling the Majorana fermions along on different sublattices. That's why you have a tau y here. This is the only difference. But it turns out this difference is crucial when determining the criticality. So it makes all the critical exponents different. Oh yeah, sure. Yep, and then we obtain the Landau damping by integrating this diagram, or by doing a RPA resummation of this diagram, and the non-analytic contribution looks rather complicated, but nevertheless, this is the only term that we kept for the propagator, and the common analytic term of the propagator and the 5⁴ is dropped. Yep. So this is what we get. And oh yes, and we also expand the theory around the critical point, which is the semi-Dirac point, where you have one linear direction and one quadratic direction in the momentum space. And we must stress that this is though we start from an Ising coupling, but this is actually general. So this whole theory should work for other magnetic interactions as well, because the low energy theory could just look like this. And to this, we did momentum shell RG, which I'll spare you with the details. But nevertheless, we just calculated the diagrams to one loop order and do the large N expansion. And this is what we get. So we get a completely different set of critical exponents comparing with the normal symmetry breaking ones. And yeah, so here we get a anomalous dimension for the fermions, which indicates some sort of breakdown of the quasi-particle picture. So we will have some kind of Majorana non-Fermi liquid. And the other exponents like the correlation length exponents will then determine the gap opening. Yeah, so the physical observables like the spin correlation will then be characterized by the anomalous dimension of the fermions. So in principle, it could be viewed, or it could be observed in experiments. So to summarize, we have studied the topological phase transition of the Kitaev model in presence of magnetic interactions with projective RG, and we have derived the general low energy effective field theory, which looks pretty much the same as, pretty similar to a semi-Dirac Grosvenor U-cover theory. But the different form of the U-cover coupling actually leads us to a completely different universality with a set of different exponents. think that's all. Thank you very much.
Very nice. Okay, so open for questions. We start. You have these two different directions. I mean, one dispersion is sort of quadratic, the other one is linear.
Yeah.
So this is preserved on RG, so that one of them is power 2, the other one is power 1.
Yes.
This is not changed.
Well, it's actually, oh yeah, the power does not
power-
change. I mean, because
only Z changes. So
yeah,
there,
because
the
we do,
power
yeah,
as
yeah,
compared to
because we do
1.
perturbative RG, that's the only thing we can get actually, because we can't really get new corrections to the powers, right? I mean, the only terms we will get has the same
Is it
structure.
obvious? I don't know. I thought it would have been possible in principle to get, you know, some different power.
No, if you do perturbative RG, I don't think that's possible.
Did you get the effect of temperature? Because in both of these gap cases, I would imagine they kind of extensify the temperature.
Yes, but we only studied this for at the main field level. So for the RG calculation, we didn't do any finite temperature calculations. Yeah, I don't have a clear answer now. Yeah, I need to think about it.
Yeah, there was-
Well, for small enough interaction, and the RG works. I think the main concern is that because we did some large n calculation here, but n is by no means large, so that could be a potential issue. But I mean, for the general Grosvenor view cover, people have calculated for like up to 4 loop diagrams, and the critical exponents sounds, well, they are pretty sound, so I think it should probably work.
Yeah, do I understand that you're predicting a new universality class of phase conditions for large enough n?
Well, yeah, that's actually
Or
hard
could
to.
there be a weakness?
Yeah, because like we have mentioned before, this is not exactly a symmetry breaking phase transition. So it looks like one. So we can, that's why we analyze it in the same
Well,
manner.
there are phase theories that do not have order. That's not necessarily.
Yeah, oh, well then,
The difficulty. That was gonna be my other question. Does your, is your phase transition a kind of confinement or deconfinement transition? Those things certainly exist in Z2. I guess I should ask, what's happening to the underlying Z2 gauge field at your transition?
yes, we have just had this discussion earlier with Frank actually, because we haven't really taken into account the fluctuations of the gauge field. So we're just, so for the gauge field degrees of freedom here, we just integrated them out simply, which could, well, potentially be
Your new terms now cause the gauge fields to fluctuate in time. That's correct. They violate. Previously the W's commuted with the half.
Yeah.
But do they no longer commute?
Yeah, that's correct.
But I think my understanding, if I may, so there were these two, there was this red line, and there's this black line. The black line is connecting two phases with the and then there is the red line on the right of which you have the other phase that is confined to the fixed. So the red line would have been the transition where
Yeah.
the gauge fields, whatever.
Yeah. This would be inside the.
This is inside.
Yeah,
This is
so-
one deconfined phase.
Okay, I did want to ask that. So this is the transition between the gapless spin liquid
And
and
the
the
gap
gap spin liquid.
Yes,
But this happens even in the absence of the Ising term.
yes, exactly. But then
So
you
does
will,
the Ising term change something? Maybe I missed it.
yeah, for our point is that if you have any sort of other kinds of magnetic interaction, this is the universality you will get. But for
Okay.
pure Kitaev, actually there's no, it's a pure Majorana, it's free Majorana theory.
Yeah.
So there's no interactions at all. That's why you go back to
So
this.
you're saying even the most minute part of Ising interaction is changing this universality of that transition.
Yes,
Okay.
yes.
Also, one thing, so there was also a paper by Shubokov, Shmalia, and Nagosa, where they looked at the electronic topological phase transition, which was observed in black phosphorus, and you can do ARPAS, of course, if you have real electrons. But what they did, and it was also just basically making one hopping different, like putting strain. But then they also wanted to add interactions, and they considered long-range Coulomb in this system, which is also, as you said, not breaking any symmetry. So they studied basically a very similar theory to what Huanzhi studied. But again, if you have density interactions, it looks very different to the interactions you can have here. So again, it's different critical exponents.
Cool. Okay, so I guess we had our 10 minutes discussion. Huanzhi, very nice talk. Thank you. The next talk is Joseph Chapman. So Huanzhi coming up, I'm reading out the title. So Joseph Chapman is coming from Kent.